So hello everyone, let's start the chapter Electrostatic Potential and Capacitance. Electrostatic Potential and Capacitance. It is a part of electrostatics only, and it is the second chapter of Class 12 Physics. We have covered electric charges and fields. Now we are moving to electrostatic potential and capacitance. Likewise, you have learned about the gravitational potential. Similarly, here is the electrostatic potential. So what is electrostatic potential difference? It is the difference between two potentials on two different points. So it is represented by delta V. It is like VB minus VA, potential at point B minus potential at point A, and is given by work done by external forces by upon Q naught, the test charge. The charge which is moved from one point to another, that is the Q naught. It is our test charge. And the work done by external forces gives a potential. So, getting the formula about electrostatic potential. Electrostatic potential is a potential at the one point only. Potential difference क्या था? That was the difference between two electrostatic potentials at two different points, and it was given by work done by external force by Q naught. And electrostatic potential is given by work done by external forces by Q naught. Considering the second point is at infinity, having the potential of 0. So it is simply written potential at one point, work done by external forces by Q naught. And it is also given by KQ by small r. KQ by small r square was the electric field. So potential is E dot R, because we are only multiplying small r with the electric field and getting the KQ by small r. It is its unit is volt or joule per coulomb. Why joule per coulomb? Because we are talking about work done by external forces, it is joule, and Q naught is the charge, so it is coulomb. Moving ahead, work done by external agent. What is work done by external agent is equals to, it is Q naught into delta V. इसी फॉर्मूले से हमने डेराइव कर लिया वर्क डन बाय एक्सटर्नल एजेंट इज इक्वल टू Q naught into delta V. And work done by external agent is path independent. It is not dependent on the path. And work done by external forces is used for the conservative forces only, like the gravitational force, electrostatic force. Moving ahead, we have talked about electric field is equal to minus dV by dr. How it comes? We have talked about dV, potential at a point is equal to KQ by small r. So if we are talking potential at the point is equal to KQ by small r, and we know electric field is equal to KQ by small r square. So what we get from this relation, if we are dividing R with the Q, we will get the electric field, and it is in the negative direction. What does the negative sign here tells? It tells about the electric potential decreases in the direction of the electric field. So electric potential decreases in the direction of electric field. We have already talked about the electric field direction. For the positively charged body, it is towards, and for negatively charged, it is radially outwards. So basically, electric field direction is from negative to positive. Electric field is equal to, when we talk about the graph of potential and distance, so negative of the slope of VR curve gives the electric field. Why? Because we have talked about dV by dr is the electric field, negative of the dV or dr. So if we talk about slope is also the perpendicular upon base, tan theta basically. So perpendicular will be potential and the base will be dr. So it will give out dE is equal to minus dV by dr. Let's talk about electric field when potential is given in different axes. It is given by minus dV by dr I cap minus dV by dy. It is dx in x direction, it is dy in j cap direction, and dV by dz in k cap direction. So this is the important formula you need to remember, because many students forget to differentiate with respect to different axes and get the wrong answer. So for getting the electric field, we have to differentiate potential with respect to different axes in the same axis only, and it will give the answer in the I cap, j cap and k cap form. So delta V is equals to minus integral of E vector dot dr vector. As we already know, velocity is equal to dx upon dt, change in displacement upon change in time. So when we want to calculate displacement, we calculate it by v dt, integration of velocity with respect to time. So similarly, we will get the potential difference is equal to minus integral of E dot dr. In case of non-uniform electric field, we have talked about it in our previous lecture. In case of non-uniform electric field, the net force does not equal to 0, whereas net torque may or may not be 0. Net torque may or may not be 0. This is a statement-based question, can be asked, and you have to remember this. So electric field direction was from positive to negative. Electric field direction is from positive to negative, not from negative to positive. So electric field direction is from positive to negative, you have to remember this. I have mistakenly told the opposite thing here. It is incorrect. You have to remember, in case of positive isolated charge, the electric field direction is radially outwards, not inwards. And in case of negatively charged isolated charge, it is radially inwards. So electric field direction will be positive to negative. Sorry for this wrong concept. So this is incorrect. I am leaving it here only so that you will not have any confusion. So moving ahead, what is electrostatic potential energy? So electrostatic potential energy is likewise of gravitational potential energy. It is a potential energy between two charges Q1 Q2 upon R. Work done by external forces is equal to change in potential energy for the conservative forces like the gravitational force, like the electrostatic force. As we have studied, work done by conservative forces is equal to negative of change in potential energy. You have to remember these formulas for better understanding. Moving ahead, what is electric dipole? Basically, dipole is having the two poles. Dipole means having two poles. So it is having one positive charge pole and one negative charge pole. We have talked about the electric field in the case of dipole. So moving ahead, potential at axial point. We have talked about electric field at axial point, at equatorial point, and at any point. Similarly, we will be talking about potential at axial point axial position, V is equals to Kp upon R square minus L square. L is the length of the dipole. In case of short dipole, R is much more than L. Why? Because the dipole is short, so its length will be very less. Now talking about potential at equatorial position. So at equatorial position, the potential will be 0 only. If we talk about at any point potential will be potential will be Kp cos theta upon R square. You have to remember this formula because it may be asked at any point also. Now we will be talking about work done in rotating dipole. So what will be the work done in rotating a dipole? Work done will be Pe cos theta 2, no, cos theta 1 minus cos theta 2. Why cos theta 1 minus cos theta 2? Because the work done was minus Pe cos theta. As we have remembered from the previous lecture, work done will be minus Pe cos theta, and through this the potential energy was minus Pe cos theta, and work done is negative of change of potential energy. So if we will put minus of minus Pe cos theta 2 minus Pe cos theta 1. So on solving it, we will be getting Pe cos theta 1 minus cos theta 2. So this will be the answer. Let's talk about potential energy stored in a dipole. We have talked about it here only. Potential energy is minus P vector dot E vector. Potential energy of dipole is minus P vector dot E vector. And if we open the formula, we will get minus P cos theta because it is the dot product. In case of the cross product, it will be minus P sin theta. But here it is the dot product, so it is minus P cos theta. Now talking about where is the potential energy minimum. Potential energy will be minimum minus P. It is possible when cos theta is equal to 1. So theta is equal to 0 degree. So potential energy is minimum, so it is stable equilibrium. Moving ahead, what will be the maximum potential energy? It will be plus P when theta is equal to 180 degree. So cos theta is equal to minus 1. It will give minus P, and it will be the unstable equilibrium because the potential energy is maximum. Talking about force, it is given by minus du by dr. It is the slope of potential energy and distance graph. And if the force sign is coming out to be negative, so it means force is attractive. And if force sign is positive, it will be repulsive force. Moving ahead, now let's talk about the potential energy for different shapes. So if we talk about hollow sphere, or it can be spherical shell, or the conducting sphere. Talking about it, potential at the outside point will be kq by r, similar as the electric field, it was kq by r square. In case of hollow sphere, spherical shell or conducting sphere, the electric field on the surface was 0. So we will be talking about the potential at the surface, and inside it will be constant and kq by capital R. It will not depend on the distance. It will be uniform because the charge in the hollow sphere or the conducting sphere, it is spread at the surface only. If we draw the graph for potential and distance, it will be straight till the R is equals to capital R, and then it will decrease inversely, because outside the point potential is inversely proportional to R. Moving ahead, talking about solid sphere or non-conducting sphere. In this case, the outside potential will be same as the hollow sphere only. V is equal to kq by small r. Inside the potential varies, because in hollow sphere the potential inside and on the surface was same and it was constant kq by capital R. But here inside the potential will vary, kq by 2r cube 3r square minus small r square. This formula you have to remember. When we talk about potential at surface, it will be kq by capital R. And if we talk about potential at center, it will be 3 kq by 2r. So it is basically 3 by 2 potential at surface. Potential at infinity will be 0 only. So these are the important formula you have to remember in this solid sphere or non-conducting sphere. Outside the potential will be same, the kq by small r. Inside it will be kq by 2r cube 3r square minus small r square. At the surface the potential will be the same as the hollow sphere. It will be kq by capital R, and at the center it will be 3 by 2 times of potential at surface. So basically it will be 3 kq by 2r. So from this we can see at the center it is more than at the surface. So drawing the graph of potential with distance V and R, it will give like this, because it is proportional to inversely proportional to R cube and directly proportional to the distance also. Then it will decrease inversely because outside the surface the potential is kq by small r. Remember this graph, it may be asked in the form of question. Moving ahead, what is kinetic energy? Kinetic energy Q delta V. We have talked about potential energy, it was also, we have talked about work done, it was Q delta V. So kinetic energy is also equal to Q delta V, where delta V is not the potential difference, it is the accelerating potential difference. This formula is quite easy to remember, as you have learned about the de Broglie wavelength. Lambda is equal to h upon mv is equal to h upon p is equal to h upon root 2 me. Here E is the kinetic energy and h upon 2m qv. Here delta V. So delta V is the accelerating potential difference only. So from this we can also say 2me is equals to 2m q delta V. So 2m gets cancelled. The kinetic energy is equals to q delta V. You can remember it from here also. You need to remember it in extra. Now force between dipole and charge. If we are asked about force between dipole and charge, it is inversely proportional to R cube. All the formula we are talking about force between the dipole and the charge were Kp upon R cube like. And if we talk about force between one dipole and another dipole, so force between dipole and dipole, it will be inversely proportional to R ki power 4. So let's move ahead to the another shape, that is the ring. In case of ring at center, the potential at center is equal to kq by capital R. In all the three cases, the potential at center was kq by capital R only. Potential at axis of the ring, because ring has two axes, x-axis and the y-axis, and basically the axial point and the equatorial point. So kq upon under root r square plus x square. R is the radius and x is the distance between the point and the center. Moving ahead, electric potential at the surface of an atomic nucleus. As we say, her potential at any surface is kq by capital R only. At the surface of an atomic nucleus. So atomic nucleus is also spherical in shape only. So it is given by kq by capital R is equal to k z e upon R, because q is equal to z e only. We have read about q is equal to ne in the quantization of charge in the chapter 1, electric charges and fields. So here n is replaced by z. Z is the atomic number. So n is basically the number of electrons, and atomic number is also equal to the number of protons and the number of electrons only. Moving ahead, E is equal to minus delta V upon delta R. We had talked about this. So it is basically applied for equipotential surfaces also. What are equipotential surfaces? Here the electric field is always perpendicular to the surface. So delta V we can find from here, minus E vector dot delta R vector. So potential at higher point minus lower potential is equal to E into delta R. Use it to apply on the equipotential surfaces only. Let's talk about an important formula. It is very important for the question point of view. Many times it is asked. Electric field just outside. We talked about it in the previous chapter also. Just outside the surface or on the surface of a conductor in terms of sigma. What is sigma? It is the sigma is just the charge density. So sigma is upon epsilon naught. Electric field will be equal to sigma by epsilon naught only. Moving ahead, let's move on to the another part of our chapter, that is the capacitance. So what are capacitors? These are basically the condensers. They store the energy in them. We will talk about the formula of energy and everything further. So capacitance is basically equal to, capacitance is a property of the capacitor. So epsilon naught A by D, or it's another formula is equal to Q upon V. So basically we can remember it like Q is equal to CV. Easier to remember. C is equal to Q upon V, but capacitance does not depend on the charge and the potential. It only depends on the area and the radius. Area and the distance. Moving ahead, electric field is equal to sigma by epsilon naught. Similar to electric field at the outside the surface of conductor, it is sigma by epsilon naught. Potential will be E into D, as we have talked about it. E is equal to V by R, so it is E into D. Let's talk about energy stored in the capacitor, or the energy density. What is energy stored in the capacitor? Basically the function of capacitor is to store the energy only. So it is energy stored in the capacitor is equal to half CV square. Now we have talked about C is equal to Q C is equal to Q by V. So if we put it in the formula, will be half Q square upon C. We are replacing the V by Q by C. So it is Q square by C square, and 1 C got cancelled. So we will get it half Q square upon C. And we can also write it as half into Q into V. Why Q into V? Because V is equal to Q upon C. Taking Q upon C from this formula, we will get Q into V. So you can only remember half CV square, and you can derive the formulas if you know the fundamental formulas given above. So capacitor basically stores energy. But how it stores energy? It stores energy in the form of electric field. It stores energy in the form of electric field. What is the energy density? It is basically energy stored per unit volume. Energy density means energy stored per unit volume. Energy by volume. So it will be half epsilon naught E square. Remember, do not get confused between epsilon naught and E. E is the electric field, and epsilon naught is the permittivity of free space. So if we talk about capacitor, like we have talked about the electric field and the electric force. In case of dielectric inserted, so force varies, like F dash was equal to F by K. K was the dielectric constant only. So force was decreasing by K times. In case of capacitor with dielectric, basically the capacitance increases by K times, and it is obtained as Ka epsilon naught by D. K is the dielectric constant only. So in case of electrostatic force, the force was decreasing K times. Here the force is capacitance is increasing by K times, and all the formula is remaining the same. Talking about electric field, net electric field, it will be firstly it was sigma by the epsilon naught. So electric field will decrease by K times, because F is equal to Q into E. Force was decreasing by K times, so electric field will also decrease by K times. Talk about induced electric field. Because of the inserting the dielectric, the electric field will get induced sigma by epsilon naught 1 minus 1 by K. This is the formula you have to remember. Now talk about inserting dielectric in capacitor without battery. Inserting dielectric in capacitor without battery. What does the battery do? It maintains a constant potential difference across the capacitor. But in case of without battery, the capacitance will increase K times. So it will be K epsilon naught A by D. Electric field will decrease K times, so E will be E by K, sigma by epsilon naught K. Potential will change by K, it will be decreasing by K, because Q is equal to CV. Charge always remains constant, capacitance is increasing, so potential will decrease. So it will be V by K, sigma D by K epsilon naught. How we are writing the potential as sigma D by K epsilon naught? Sigma by epsilon naught is basically our electric field, and the E dot dr is the potential. So we have written sigma D by K epsilon naught. Talking about the potential energy, it will be half q square upon c. It was the normal potential energy. Now q will remain constant and c is increasing, so it will be q half q square upon kc, because capacitance is increasing k times, so we have written it with k times. Capacitance is increasing k times. So what we have to remember from here, these are very important statements you have to remember from here. Charge on capacitor plates, we are talking about without battery. So charge on capacitor plates remain constant. As we have seen, the q is remaining the constant, and because c was increasing, so v was decreasing, and electric field decreases k times. As we know, the force increase on inserting the capacitor, on increasing the dielectric, the force was decreasing k times. So here also the electric field is decreasing k times, so we can say that here the potential is decreasing k times. So because potential is decreasing k times, and E is equals to E dot dr is equals to V. So potential is decreasing k times, so electric field will also decrease k times. So electric field decreases by k times. We have talked capacitance will increase k times. And energy stored decreases k times. Why? Because the capacitance was increasing k times, so and the charge was remaining constant, so keeping it in the formula half q square upon c, so c will become kc. Moving ahead, let's talk about another part of it, dielectric constant. Dielectric is inserted with battery. A battery is placed here, so the potential will remain the same. So let's see, capacitance will as usual increase k times. It will be k a epsilon naught by d. So you have to basically remember capacitance always increases by k times in case of battery or in case without battery. Q dash, here the charge is getting changed. Why? Because q is equal to cv and c is getting changed, so q will be kcv, k times of cv, because potential is remaining the same. Why? Because battery is remaining connected. Let's talking about potential energy stored, it will be half cv square. Now the potential is remaining the same and the capacitance is increasing k times, so potential energy will energy stored in the capacitor will increase k times. So we can write it, capacitance increases by k times, potential difference remain constant. Why? Because battery is remaining connected, so it will not alter the potential difference. In the last part, when there was no battery connected, so it was potential difference was decreasing by k times, and so as the energy was decreasing by k times, energy stored was decreasing k times, and the charge was remaining constant. But here charge increases k times because of the increase in capacitance by k times, and the energy stored in this case increases by k times, whereas in case of without battery it was decreasing by k times. So moving ahead, if we will given without battery case, so energy stored formula we have to use is half q square upon c. Why q square upon c? Because here the q remains the constant. So we will take the one variable system only. In case of with battery, here the potential remains the constant, so we will use U is equal to half CV square, because only C is varying here, V is remaining the constant. Let's talk about force on the plates of capacitor. Force on plates of capacitor. As we have talked about, the electric field on the capacitors will be sigma by epsilon naught. So basically sigma is Q by A epsilon naught. So we have to got the force. Force is equal to Q into E. So it will be Q square upon A epsilon naught. Because we are talking about the force on the plates, it will be electric field of one plate will be sigma by 2 epsilon naught. So it will be 2 epsilon naught. So force will be Q square upon 2A epsilon naught, or we can write it as sigma square A upon 2 epsilon naught. Sigma square A, how? Because sigma square is equal to Q square upon A square. We need here A square, so we are multiplying here with A. So we will multiply upper portion, the numerator with A also. Let's talk about capacitance. When the dielectric of thickness T is inserted, so it will become A epsilon naught upon D minus T plus T by K. This formula you have to remember only. This is a very important formula. Directly you will be given the dielectric constant, anything, and the thickness of the dielectric constant T, and D is the A epsilon naught by T. D is the distance between the capacitance plates. So in case of air, the K is equal to 1. In case of metal or conductor, if it is not giving K value, so or it is mentioned it is placed in air, or it is placed in metal or conductor, so K will be infinity in case of metal or conductor. Moving ahead, its formula can be, if more than one dielectric is placed, it will be D minus T1 plus T2, thickness of both the dielectrics, plus T1 upon K1 plus T2 upon K2. Basically you have to remember the main formula only, and here the T will become T1 plus T2, and the T by K will become T1 by K1 plus T1 by T2 by K2. Moving ahead, let's talk about series combination of capacitors. So series combination में क्या होता है, रेजिस्टेंस की सीरीज कॉम्बिनेशन में द करेंट रिमेन्स द सेम. उसकी वजह से जो है हम पोटेंशियल डिफरेंस के बेसिस पे आर इक्विवेलेंट निकाल लेते हैं, R1 प्लस R2 डायरेक्टली ऐड करते हुए. नाउ इन केस ऑफ कैपेसिटेंस सीरीज कॉम्बिनेशन में it is opposite of the resistance. Here the parallel resistance formula is used in case of series capacitance. 1 upon C1 plus 1 upon C2 plus 1 upon C3. Basically Q is equal to C equivalent into V. So V is equal to Q upon C equivalent, and in case of series capacitance, potential will remain the same. Potential will vary, so we will add the potential difference only. Q will remain the same. Similarly, in case of the series resistance, the I was remaining the same, the current will remaining the same. Here the charge is remaining the same. Charge is remaining the same, potential is changing, so we will be adding the potential. In case of resistance, it was V is equal to IR. So R equivalent was R1 plus R2. Similarly, in case of here, we are using V is equal to V1 plus V2. But here V is equal to Q upon C equivalent. So C equivalent will be 1 upon C1 plus 1 upon C2. In case of identical capacitance, it will be C by N. In case of two capacitance only, we will use similarly in case of parallel resistance formula C1 C2 upon C1 plus C2 for easy calculations. In case of parallel combination of capacitance, we will use C equivalent is equal to C1 plus C2 plus C2 plus C3. and C equivalent in case of n identical capacitance will be n into C. Why this formula is being used? Because in case of parallel the potential will remain the same, so Q will be changing, so we will be using Q is equal to C equivalent into V. Now the V is remaining the same, Q is changing, so C equivalent will be Q1 plus Q2 plus Q3, and similarly it will be C equivalent will be C1 plus C2 plus C3. So let's talk about spherical capacitor. So till now we were talking about the parallel plate capacitors. These were the two plates of the capacitor separated by some distance and having the two charges. So these were the parallel plate capacitors. Now we are talking about spherical capacitor. Basically you have to only learn the formula of the capacitance of a spherical capacitor and its energy stored. So it is C is equals to 4 pi epsilon naught R, and U will be Q square upon 8 pi epsilon naught R. So basically U is equals to Q square upon 2C, as we have learned in the previous slide only. U was half Q square upon C, so we are applying the formula here and getting this like this. It can be K Q square upon 2R, because K is 1 upon 4 pi epsilon naught, and here it is given 8 pi epsilon naught, so 2 is keeping here. Q square by R is kept as it is. Let's talk about Kirchhoff's law. Kirchhoff is giving the junction law and the loop law. So we will be learning more about it in the current electricity chapter, but we have the basic idea here. Junction law is based on conservation of charge. Where is the loop law? It is the Kirchhoff. Kirchhoff first law. Loop law is the Kirchhoff second law. Basically it is based on conservation of energy. It is known as conservation voltage law, Kirchhoff voltage law. It is known as Kirchhoff charge law. Moving ahead, junction potential. So potential at the junction is very commonly asked question in our paper. It is C1 V1 plus C2 V2 plus C3 V3 upon C1 plus C2 plus C2. So basically potential at junction is equals to charge at junctions, their summation upon capacitance summation. Moving ahead, when two capacitors are connected, they can be connected in opposite polarity or in the same polarity, as we have talked about, and we will be talking about different cells connected in opposite polarity or the same polarity, what will be the EMF. So here, when capacitors are connected in same polarity, so common potential will be C1 V1 plus C2 V2 upon C1 plus C2. Similarly, energy loss if we have to calculate, so it is basically half CV square, V final square minus V initial square, but here the capacitance is also changing, so it is half C1 C2 upon C1 plus C2 into V1 minus V2 का whole square, because the capacitance was changing, so we have expanded it. Final energy is equals to half C1 plus C2 into V dash square. And now let's talk about when capacitors are connected in opposite polarity. So in case of opposite polarity, V dash is equals to Vc, common potential C1 V1 minus C2 V2 upon C1 plus C2. Here the minus sign has come here only, not the denominator. So what will be the energy loss? It will be similar, only the minus sign will be changed with the positive sign. It will be half C1 C2 upon C1 plus C2 into V1 plus V2 का whole square. So final energy will be half, they will be similar, C1 plus C2 into V dash का whole square. Now talking about percentage energy loss. This formula can be used in both the cases. It is the general formula. The energy loss, we have talked about energy loss in both the cases. Upon initial energy, we know the initial energy is half CV square into 100. So it is the percentage energy loss formula. So this was all about the chapter electrostatic potential and capacitance. We have completed it in 45 minutes. I hope you understand this chapter, and stay tuned for further updates and revision classes. Thank you for listening me out. Have a great day.